welcome to another deep dive. This time, we're taking a closer look at Rydberg atoms.
Rydberg atoms.
These are atoms that, they have electrons that orbit millions of times further out than what we'd normally expect.
Yeah, they're fascinating. They're like the giants of the atomic world, straddling this line between, what we think of as familiar in physics, but then some really strange properties.
Right. And we're going to get into why these oversized atoms are so strange.
Yes.
And how scientists think we can use them for things like quantum computing and deep space exploration even. So
absolutely.
Buckle up. It's going to be a wild ride.
It is. What captivates me about these atoms is that, like you said, these electrons are in these incredibly distant orbits, making them almost the size of a small living cell, you know? But the crazy part is a lot of their behavior can be understood with the same physics that we apply to something as simple as hydrogen.
Really? Wow.
Yeah.
That's pretty wild.
Yeah.
I'm looking at figure 1 from the Wikipedia article right now, and the electron orbital of a Rydberg atom is huge GE.
Oh, yeah. Is this what makes them so sensitive to electric and magnetic fields?
That's a great question, and yes, it plays a huge role.
Okay.
You see, because the electron is so far out, it's experiencing a much, much weaker pull from the positively charged nucleus.
Right, okay.
Like, imagine this. If you're holding a magnet close to a piece of metal,
okay,
the traction's super strong.
Yeah.
But as you move it further away, the force weakens dramatically.
Right.
It's the same thing here. The electron's so distant that even a tiny electric or magnetic field from outside can shift its orbit and energy.
Oh, okay. So it's like they're really delicate, really susceptible to any little nudge.
Yeah, that's a good way to put it. They're fragile.
Okay.
It's a double-edged sword, though, that sensitivity. It makes them very difficult to work with.
Yeah.
But on the other hand, it makes them really, really useful for things like sensing where we need extreme precision.
Oh, wow.
Yeah. So how did scientists even discover these things? I mean, it seems like a pretty big jump to go from studying basic atomic spectra to realizing there are these giant atoms lurking out there.
You're right. A lot of times in science, it's a gradual process. We take one step at a time. It all started in the late 1800s with Johann Balmer and Johannes Rydberg.
Right.
They were studying the light emitted by hydrogen, and they came up with formulas that described these patterns.
Okay.
It was essentially uncovering the mathematical fingerprint of atomic energy levels.
So they were like laying the groundwork for understanding how electrons are arranged.
Exactly.
Okay.
But it was Niels Bohr who came along and really connected those dots.
Yep.
He took their formulas and he used his new model of the atom, where electrons are in specific orbits, to explain those series. He realized that these higher energy levels described by the Rydberg formula, well, those were the ones corresponding to the electrons that are in these distant orbits.
Wow. So they were piecing together like atomic structure just by looking at the patterns in the light.
Exactly.
Wow, that's incredible.
Yeah, this paved the way for quantum mechanics, which gave us a much more complete picture of the atom.
Okay, so we've got these giant atoms. They have super sensitive electrons. How do we even create these things in the lab?
Yeah, it's not an easy task.
Right.
You're right. It's a delicate process. So we need to give the electron a specific amount of energy to push it up to that higher level. And one way to do this is called electron impact excitation.
Okay, is that where we fire electrons at atoms and just kind of hope for the best?
Well, it's a bit more controlled than that.
Okay.
But you have the right idea. We use a beam of electrons, and we can fine-tune the energy of that beam.
Okay.
When an electron from that beam hits an atom, there's a chance it will transfer just enough energy to boost the atom's electron up to a Rydberg state.
So it's like we're playing a really tiny game of pool.
Yeah, exactly.
Yeah,
trying to make that perfect shot.
Yeah. And knock that electron right where we want it. Cool.
Right. But there are other more precise methods. One is called charge exchange excitation, and this uses ions.
Oh, okay.
So these are atoms with an electric charge.
Wait, are we talking about swapping charges between atoms?
That's exactly what we're talking about.
Wow, okay.
We pick ions carefully so that when they interact with neutral atoms, we have a really high chance of transferring an electron and creating that Rydberg atom.
So we've got the chaotic pool method, and we've got the charge swapping method. What else is in our toolbox here?
Well, the most precise method is called optical excitation, and this is where we use lasers.
Okay.
To deliver that precise amount of energy needed to push the electron up into the Rydberg state.
Okay, that makes sense. Lasers, they're very precise.
Exactly.
So it seems like that would be the ideal tool, but I'm guessing there are limitations.
You're absolutely right. Optical excitation is limited usually to certain types of atoms, like alkali metals. And that's because they have a lower energy requirement to get those Rydberg states. Think of it like giving someone a gentle push on a swing versus trying to launch them into orbit. Some electrons are just more willing to be pushed out further.
Right, okay. So we've got these Rydberg atoms, the giants of the atomic world, incredibly sensitive, created through these really elaborate processes. What makes them so special? What can we learn from them?
Well, that's where things get really interesting. Despite their immense size, Rydberg atoms, especially those of alkali metals, behave a lot like hydrogen.
Really?
Yeah.
But hydrogen is the simplest atom there is.
hmm
How can these behemoths be acting like hydrogen?
Well, think about it this way. The electron in a Rydberg atom is incredibly far away from the nucleus.
Mhm.
From its point of view, it really only sees the nucleus and that +1 charge, just like in hydrogen.
Oh, okay.
All those inner electrons are basically shielding that outer electron from the full nuclear charge.
So it's like this Rydberg electron is living in its own little hydrogen world. Doesn't even know about all the complexity going on inside the atom.
Exactly. That's a great way to think about it. And this means that we can understand and predict their properties using the hydrogen atom as a model.
Oh, okay.
It's really powerful. We take a simple framework and apply it to what looks like a really complex system.
But I'm guessing it's not a perfect one-to-one match, right?
Okay. You're absolutely right. There are some differences. Those inner electrons that we talked about, they do have some influence,
Yeah.
and that results in small corrections to the energy levels, and we call these quantum defects.
Okay, so the hydrogen model is like a good starting point, but then we have to factor in those quantum defects.
Exactly. And those defects can actually tell us a lot about the structure of the atom and the interactions within the atom. They're like little clues that can help us unlock the complexities of these atoms.
Oh, that's pretty neat. Okay, so we've gone from the basics of Rydberg atoms, what they are, how to create them in the lab, and this surprising connection to hydrogen. I'm really excited to dive deeper into this
Yeah.
and see what makes them so exciting for, things like quantum computing and deep space exploration.
Absolutely. There's a lot more to discover, and those quirks are what make them so interesting for applications. Remember how we talked about their sensitivity to electric fields?
Yeah. They're like those electroscopes we used back in school,
Mm.
but like a million times more sensitive.
It's a good analogy. But the underlying physics is even cooler. So the electron in a Rydberg atom is so far out that it has what we call a really big electric dipole moment.
Okay, remind me, what's a dipole moment again? It's been a while since physics class.
Okay, so imagine you have a positive charge and a negative charge, and they're separated by some distance.
Okay.
That separation, that creates what we call an electric dipole moment. And in a Rydberg atom, well, the electron's way out there, and the nucleus is positive, so they form this dipole.
So the bigger the atom, the bigger the dipole moment, and the more sensitive it is.
That's exactly right. And we're not talking about just tiny changes here. Even a relatively weak electric field can cause some really big energy level shifts.
Oh, wow.
This is called the Stark effect.
Stark effect? Okay. So the electric field, it's like distorting the electron's orbit and changing the energy.
Exactly. And we can really precisely control that distortion.
Oh, wow.
We can use electric fields to very carefully tune the energy levels of these atoms, which opens up a lot of cool possibilities.
Like what could we do with that?
Well, think about sensors. We could detect incredibly weak electric fields, like fields so weak that they'd be completely invisible to normal sensors.
Oh, wow. That'd be revolutionary. What kind of applications?
Well, think about medical imaging. We could map electrical activity in the brain or the heart in much greater detail than we can today. Or telecommunications, more sensitive receivers that can pick up even the faintest of signals.
Wow. So these giant atoms could be the key to some pretty groundbreaking tech.
That's right.
Yeah.
And that's just the beginning. There's this other really interesting thing called the Inglis-Teller limit.
The Inglis-Teller limit. Okay, I'm intrigued. What's that?
Okay, so as we make the electric field stronger, the Stark effect causes the energy levels to shift. But at a certain point, they get so close together that they would cross if they weren't coupled.
Oh, okay. So it's like they're on a collision course, but something's stopping them from crashing.
That's a great way to think about it. And the Inglis-Teller limit, well, it describes the maximum electric field strength you can have before that happens.
Okay, so we're like pushing the boundaries of quantum physics here. This is getting pretty deep.
Yeah.
Okay, so we've talked about single Rydberg atoms, and they're really sensitive. But what happens when we bring a whole bunch of them together?
Well, that's when things get really strange. We enter the realm of Rydberg matter.
Rydberg matter. Okay, that sounds like something out of like a sci-fi novel.
It kind of is. It's this really bizarre state of matter. It forms when a bunch of Rydberg atoms, they start to clump together.
Okay, so they get all cozy and form these little atomic clusters.
Exactly. And these clusters, they don't behave like a solid or a liquid or a gas. It's more like a dusty plasma with these little clusters of atoms dispersed throughout the gas.
Oh, wow. That's wild. What's so special about these clusters?
Well, one thing is their structure. They're usually hexagonal and planar,
Okay.
kind of like tiny, flat snowflakes, but made of atoms. And what's even crazier is that their size is limited by the speed of light.
The speed of light is limiting how big they can get. How is that even possible?
Well, it all boils down to how atoms interact. They use electromagnetic forces, right? And Einstein showed us that those forces can't travel faster than light, so there's a limit to how fast information can be exchanged within the cluster, and that limits how big it can get.
So relativity is affecting things even on the atomic level. It's like, wow.
Yeah, it's pretty amazing. And another interesting thing is that Rydberg matter, it's surprisingly stable. It doesn't easily decay like most excited states of matter.
So these clusters can, like, hang out for a long time. How long are we talking?
Potentially billions of years.
Billions of years. That's incredible. What's the secret to that?
Well, we're still figuring that out, but it seems like the way they interact in these clusters creates a kind of protective barrier that prevents them from decaying.
So we've got giant atoms,
Yeah.
super sensitive to electric fields, and now this incredibly stable form of matter. What can we actually do with all of this? I'm guessing this is where those applications like quantum computing and deep space exploration come in.
You got it. Let's start with quantum computing. One of the biggest challenges in building a quantum computer is finding a way to create and control qubits.
Okay, qubits, I've heard of those.
So these are the quantum version of bits, which are the zeros and ones in our classical computers.
Right.
And Rydberg atoms are showing a lot of promise for building qubits.
Okay, I'm all ears. How do they fit in?
Well, remember how we talked about those strong interactions and their sensitivity to electric fields?
Yeah.
Those are exactly what we need for qubits.
Okay. We can use electric fields to carefully manipulate the energy levels of Rydberg atoms, and we can create entanglement between them. And that's crucial for doing quantum computations.
Entanglement. That's another one of those quantum things that always makes my head spin.
Yeah.
What is it again?
Okay, so think of two coins flipped at the same time. They could both land on heads, both on tails, or one heads, one tails, right?
Right.
In the quantum world, entanglement is like flipping two coins that are linked. It doesn't matter how far apart they are. If you look at one coin and it's heads, you instantly know the other one must be tails.
So it's like they're sharing some kind of secret information, even across vast distances.
That's a good way to think about it.
Yeah.
And that's really important for quantum computing. Rydberg atoms, with those long-range interactions, make it easier to create and control those entangled states.
Wow. So we could build quantum computers out of these giant interacting atoms. That's the idea. It's an exciting field with a lot of potential. Now, shifting gears a bit to astrophysics. Did you know that Rydberg atoms are found in interstellar space?
Wait, really? These giant fragile atoms are out there in the vastness of space.
They are, and they actually tell us a lot about what's going on out there. So Rydberg atoms, they emit radio waves at very specific frequencies. We call these radio recombination lines.
So they're like sending us radio signals from space.
That's a fun way to think about it. Astronomers use radio telescopes to pick up these signals, and they give us a ton of info about the density, temperature, and composition of gas clouds out there.
So they're helping us probe the mysteries of the universe. It's incredible.
Yeah.
We've gone from basic atomic properties to quantum computing and now astrophysics. It's like Rydberg atoms bridge the gap between, the tiny world of atoms and the grand scales of the cosmos.
You've got it. And there's one more thing I want to mention. Deep space exploration. Remember their sensitivity to electric and magnetic fields? Wow, that makes them perfect for sensors, really sensitive ones that we could use on spacecraft.
Okay, I see where you're going with this. We could use them to study other planets and moons.
Exactly. Imagine a probe with Rydberg sensors orbiting a moon like Europa, which we think has an ocean under its surface.
Okay.
We could map its magnetic field with amazing detail, and that could tell us about the composition of its ocean.
Oh, wow. So we're using atoms to peer beneath the surface of alien worlds.
Pretty cool, right? And that's just one example. We could study atmospheres, magnetic fields, even search for signs of life.
Wow. The possibilities are endless.
It's a really exciting time to be studying Rydberg atoms.
Okay, my mind is officially blown.
Yeah.
We've gone from what they are to their crazy properties to their potential for, revolutionizing fields like quantum computing, astrophysics, deep space exploration. I mean, the range of applications is just incredible.
It is. It really makes you wonder, what else is out there? What other discoveries are waiting to be made?
I know. It's like we've just scratched the surface. So many possibilities. What are some of the things that researchers are working on right now with these atoms?
Well, one area that's particularly interesting is Rydberg atom lasers.
Rydberg atom lasers. Okay, that sounds pretty wild. How do you even make a laser out of these things?
So to make any laser, the key is something called population inversion.
Okay.
And that means we need more atoms in an excited state than in their ground state. This creates the conditions for stimulated emission where a photon can hit an excited atom and it triggers that atom to release another photon. And they'll have the same energy and direction, so it amplifies the light.
Oh, okay. So it's like this chain reaction of photons.
That's right. And Rydberg atoms, with their unique energy levels and their long lifetimes, they're great for creating these population inversions.
Interesting. Would these Rydberg lasers be, I don't know, like different from regular lasers in some way?
Yeah, potentially. They could operate at very different frequencies. For example, the terahertz range. That's a frequency range that's really difficult for our current lasers to reach. And they could be more efficient, maybe even have some unique properties that could lead to new applications.
Terahertz. Okay. What kind of things could we do with lasers like that?
Well, terahertz radiation is really useful for things like imaging, sensing, and communications. Imagine, being able to see through walls using terahertz waves, or transmitting data at super high speeds.
It sounds like science fiction. Almost every time we talk about these atoms, it's like we're pushing the boundaries of what's possible. What else is out there? What else is on the horizon?
Another thing that's really fascinating is using Rydberg atoms to simulate other quantum systems.
Oh, okay. I've heard of quantum simulations. How do they work, and why are Rydberg atoms good for that?
Well, think about it this way. If you want to study a complex system, like a superconductor, these systems have tons of interacting electrons. And modeling them on a classical computer is incredibly difficult.
Yeah, it's almost like trying to predict the weather, but with way more variables.
That's a good analogy. But with quantum simulations, we can use qubits instead of bits.
Okay.
And those qubits, they can be in superposition states and they can be entangled. So we're using quantum mechanics to directly simulate the system we want to study.
So it's like building this quantum playground with these Rydberg atoms, where we can control them and learn about other quantum systems.
Exactly. And with Rydberg atoms, we can really finely control their interactions, their energy levels, which makes them perfect for building these simulators.
Wow. So it's like a whole new way of doing science. Instead of just observing, we can actually manipulate things at the quantum level.
That's right. It's pretty revolutionary.
Absolutely. What kind of things could we discover?
Well, for example, we could maybe finally understand high-temperature superconductivity, something that's been a mystery for a long time. Or we could even design new materials with specific properties that we want.
Oh, that's amazing. It's
Yeah.
like we're entering this new era where we're not just observing nature, but actually controlling it at the most fundamental level.
Yeah. And the exciting thing is we're just getting started. Who knows what we'll discover as we explore Rydberg atoms even further?
This deep dive has been incredible. We've talked about what Rydberg atoms are, these bizarre properties they have, and how they could change fields like quantum computing, astrophysics, deep space exploration. It's mind-blowing.
It really is. They're so versatile. The number of potential applications is just staggering.
Absolutely. To our listener, what really stood out to you? What sparked your curiosity?
Yeah, was it their size? The sensitivity that makes them so good for sensors?
Right, or maybe that strange connection to hydrogen, or the mind-boggling idea of Rydberg matter.
Or perhaps it was the potential they have in quantum computing, helping us understand the universe or exploring distant worlds. We hope this deep dive has left you wanting to learn more about this incredible area of science.
And here's one last thought for you to think about. Imagine a future where we have sensors based on Rydberg atoms everywhere. They could detect the tiniest changes in the environment, or even pick up signals from the far reaches of space.
A future where we have quantum computers powered by Rydberg atoms, helping us to tackle some of the biggest challenges we face, from developing new medicines to solving the mysteries of the universe.
It's a future that's full of possibilities, and it all comes back to these incredible atoms, these giants of the quantum world. We're only just beginning to understand their full potential. Thanks for joining us on this deep dive.